Sometimes it is useful to use a different representation to write qubits. This is known as the block sphere representation. It only works for one qubit and not for many. Let's imagine that instead of using the standard basis, 0 and 1, we associate the 0 to the up direction and the 1 to the down direction. Let's now expand our state, and then instead of writing it as usual in terms of complex numbers alpha and beta, we will write out such states in terms of a global phase, e to the I times gamma, an angle theta away from the z-axis, and an angle phi away from the x-axis. The global phase is not interesting to us, because if we measure the state, then the probabilities of getting measurement outcomes do not depend on this phase, so we cannot see it. If we write the state in this form, we can think of every state thus as being described by two numbers, theta and phi, which give us a point on the sphere. This is known as the block sphere representation. For example, for the state plus, this representation is particularly easy. Phi is 0, and we can easily see that the point is here on the x-axis. Let's now focus on qubits for which the angle phi is 0. Since we ignore the global phase, this means that the qubit is characterized by only one number, namely the angle theta. Now the y direction doesn't matter. So we can draw a simplified picture where we just have the up direction z and the direction x, and the qubit is parameterized by the angle theta. This simplified version is also known as the xz plane. If we say that the qubit is in the xz plane, it means that we are precisely in the case where phi is equal to 0, and we again ignore the global phase.